This is part 2 of liquid states and liquid crystals, and we were doing some important results related with the process of evaporation. First was cooling caused by evaporation. Second was factors affecting vapor pressure, which we have done earlier in the part 1. Now we are going to do the third part, that is boiling point. As stated above, the vapor pressure of a liquid increases as the temperature is increased. The temperature at which the vapor pressure of the liquid becomes equal to the external pressure, that is the atmospheric pressure, is called the boiling point of the liquid. When the atmospheric pressure is normal, atmospheric pressure that is 760 mm, the boiling point is called the normal boiling point. For example, normal boiling point of water is 100 degrees Celsius. The normal boiling point for any liquid is obtained from the vapor pressure temperature curves as shown for acetic acid. Obviously, if the external pressure is higher, more heat will be required to make the vapor pressure equal to the external pressure, and hence higher will be the boiling point. Similarly, if external pressure is decreased, the boiling point is lowered. This is the reason that a liquid boils at a lower temperature on the top of a mountain where pressure is low than the seashore. Fourth point is heat of vaporization, that is denoted by delta HV. When the liquid starts boiling, if extra heat is supplied to the liquid, it is used up not in increasing the temperature of the liquid but to overcome the intermolecular forces of attraction existing in the liquid and thus changing the liquid into vapor. Hence, the temperature remains constant till whole of the liquid changes into vapor. The amount of heat required to change 1 mole of liquid into its vapor at the boiling point is called heat of vaporization of the liquid. Obviously, greater the intermolecular forces of attraction present in a liquid, greater is the heat of vaporization. For example, the heat of vaporization of water is more than that of ethene, acetone, benzene, etc. Fifth is relationship between boiling point and critical temperature, that is Goldberg's rule. Goldberg's rule in 1890 pointed out the following general relationship between the normal boiling point, that is denoted by TB, and the critical temperature denoted by TC of the liquids, where TB is equals to 2 by 3 multiply TC. That is, the normal boiling points of the liquids are nearly two-thirds of their critical temperatures when both are expressed on the absolute scale. Sixth is relationship between boiling point and heat of vaporization, that is Troton's rule. Trotons in 1884 observed the following generalization about liquids which are non-associated and which do not have too high boiling points, where delta HV divided by TB is equals to 21, where delta HV is in calories and TB is in degrees absolute. This is known as Trotto's rule and may be stated as follows. For liquids which are non-associated and do not have too high boiling points, the ratio of heat of vaporization expressed in calories to the boiling point expressed in degree absolute is approximately 21. Now next topic is measurement of vapor pressure. The various methods used for the measurement of vapor's pressure are generally classified into two categories. That is, first is static method and second is dynamic method. These methods have been so named because in the static method the liquid is allowed to establish its vapor pressure without being disturbed, while in dynamic method the liquid is disturbed either by boiling it or by passing a stream of inert gas through it. Some commonly employed static and dynamic methods are briefly discussed below. First static method, A part, is barometric method. In this method, two barometric tubes are used. These are filled with mercury and then inverted into the same through of mercury. One tube is used for comparison with the other. In one of the tubes, the experimental liquid, free from dissolved air, is introduced a few drops at a time. It evaporates into the space above mercury. More and more of the liquid is introduced till no more liquid evaporates and remains as such. The difference of levels of mercury in the two tubes is then the vapor pressure of the liquid at the room temperature. For finding the vapor pressure at any other temperature, the barometric tubes are surrounded by a heating jacket. B part is isoteniscope method. This method was devised by Smith and Menzies in 1910. It is a convenient and accurate method which can be used to measure the vapor pressure over a range of temperatures. The apparatus the main part of the apparatus is the isotenoscope, which comprises of bulb B and U-shaped portion of the tube C. The bulb B is nearly half filled with the liquid under investigation, and the same liquid is placed in the U-shaped portion with its level about 2 to 3 cm below in the bulb. The isoteniscope is placed in the thermostat A, whose temperature can be noted from the thermometer T. The isotenoscope is then connected to the rest of the apparatus, which comprises of a barometric tube D and a big bottle E. The bottle E can be connected to the atmosphere or to the vacuum pump as desired to regulate the pressure inside the apparatus. The method involves the following steps. First step, the bottle E is connected to the vacuum pump and the apparatus is evacuated till the liquid boils vigorously in the bulb B. This expels all air from the isotenoscope BC. The level of the liquid in the limb L2 stands higher than in the limb L1. Second point is that the temperature of the thermostat is now adjusted to the desired value and air is admitted slowly into the apparatus by connecting the bottle E to the atmosphere till the levels of the liquids in both the limbs L1 and L2 are equal. Under these conditions, the pressure in both the limbs L1 and L2 pressure in the limb L1 is the vapor pressure, whereas in the limb L2 is equal to the pressure in the rest of the apparatus and is equal to the atmospheric pressure in centimeter minus the height of the mercury column in the tube D in centimeter. Hence, this difference is the vapor pressure of the liquid at the temperature of the thermostat. By fixing the temperature of the thermostat at any desired value, the vapor pressure can be measured at that temperature by repeating the process as described above. The second method is dynamic method. The simplest dynamic method is based upon the principle that a liquid boils at the temperature at which the vapor pressure becomes equal to the external pressure over the liquid. Thus, by fixing the external pressure over the liquid at different values, the boiling point of the liquid is determined at each external pressure. Suppose the boiling points are T1, T2, T3, etc. at the external pressure at the temperature T1, T2, T3, etc. respectively. By plotting the pressures against the corresponding temperatures for any particular liquid, a curve of the type shown is obtained. From this curve, the vapor pressure at any temperature can be found. Thus, the dynamic method differs from the isotenoscope method in aspect that whereas in the isotenoscope method the temperature is fixed first and then the vapor pressure is measured. In the dynamic method, the external pressure is fixed first and then the liquid is heated to find the temperature at which it boils. Third method is gas saturation method. The basic principle of this method is briefly described below. A known weight of the experimental liquid is taken in a closed vessel. A known volume of the dry air at a known pressure and temperature is passed through it. As a result, the molecules of the liquid are carried with the air and a loss of weight of the liquid occurs. Air is continuously passed till there is no further loss in weight of the liquid, keeping the pressure P constant throughout. The air gets saturated with the vapor. In the air saturated with the vapor, if the N1 and N2 are the number of moles of the vapor and air respectively, then the partial pressure of the vapor, which is equal to the vapor pressure of the liquid at the experimental temperature, will be given by P is equals to N by N1 plus N2 multiply P. If W is the loss in weight of the liquid and capital M is its molecular mass, then N1 is equals to W upon M. Further, if air is supposed to be an ideal gas, then N2 is equals to PV by RT. Substituting the values of N1 and N2 in equation 1, the vapor pressure of the liquid can be calculated at the desired temperature. Now next topic is surface tension. Definition first of all. Surface tension is a characteristic property of liquids which arises due to the fact that the molecules of the liquid at the surface are in different situation than those in the interior of the liquid. For example, a molecule lying inside the liquid is surrounded by other molecules and so is attracted equally in all directions. Hence, the net force of attraction acting on the molecule is zero. However, a molecule lying at the surface is attracted more by the molecules lying in the bulk of the liquid than the molecules lying above in the vapor phase. Thus, a molecule lying at the surface experiences a net inward attraction. As a result of this inward pull on the molecule lying at the surface behaves as if it were under tension, like a stretched membrane. Hence, this property of liquids is called surface tension. The surface tension of a liquid is defined as the force acting at right angle to the surface along 1 centimeter length of the surface. Thus, the units of surface tension are dynes per centimeter or newtons per meter. Further, as a result of inward pull on the molecules at the surface of the liquid tends to contract to the smallest possible area for a given volume of the liquid. It is for this reason that the drops of a liquid are spherical because of a given volume. A sphere has minimum surface area. To increase the area of surface, some work has to be done against the inward pull. For example, consider a soap solution film contained in a rectangular wire frame ABCD in which the side CD is movable. In order to extend the surface area of the film, the movable wire has to be pulled from position CD to position EF. Thus, some work has to be done against the force of surface tension. The work in ERGS required to be done to increase or extend the surface area by 1 square centimeter is called surface energy. The units of surface energy are therefore ERGS per square centimeter or joules per square meter, that is a joule meter per meter square. In SI system, surface energy is equals to work per square centimeter, that is equals to force multiply length per square centimeter equal to dynes multiply centimeter divided by centimeter square. These units are the same as those of surface tension. Thus, the surface energy is same thing as surface tension. Hence, the definition of surface energy is sometimes taken as the definition of surface tension. The values of surface tension of some common liquids at 20 degrees Celsius in dynes per centimeter are given. Where liquids are taken, first of all water, its surface tension is 72.8, nitrobenzene 41.8, carbon disulfide 33.5, benzene 28.9, toluene 28.4, acetic acid 27.6, chloroform 27.1, carbon tetrachloride 26.8, acetone 23.7, methyl alcohol 22.6, ethyl alcohol 22.3, and ethyl ether 17. Some important results. Now next topic is some important results with the property of surface tensions are briefly discussed below. First, spherical shape of drops. As already explained, surface tension tries to decrease the surface area of the liquid to the minimum. The drops of liquid or the bubbles of a gas are spherical because for a given volume a sphere has minimum surface area. Second is rise of a liquid in a capillary tube. Suppose one end of a capillary tube is put into a liquid that wets glass. It is found that the liquid rises into the capillary tube to a certain height. This rise is obviously due to the inward pull of the surface tension acting on the surface, which pushes the liquid into capillary tube, as will be discussed in more detail in the methods of measurement of surface tension. It is because of the same reason that oil rises into the wick of an oil lamp or water below the surface of earth rises to the plants through the roots or ink rises in a blotting paper. It may be mentioned here that in case of liquids which do not wet glass, that example mercury, the level inside the capillary falls below the level outside. Further, whereas the upper surface of a liquid that wets glass is concave, that of mercury is convex. Such a surface is therefore called meniscus. The angle which the curved surface, that is meniscus, makes with the wall of the tube is called contact angle and is found by drawing a tangent at that point. Third is interfacial tension. If two immiscible or partially miscible liquids are taken in a vessel, then the surface tension acting along their surface of separation, that is, along the interface, is called the interfacial tension. Its value is generally intermediate between the surface tension of the two liquids, but sometimes it is less than both. This is due to the fact that at interface, the molecules of one liquid are attracted by the molecules of the other. In fact, the surface tension of the liquid is also an interfacial tension, the two phases involved being the liquid and the vapor above it. Fourth, surface active agents. There are certain substances called soaps, certain sulfonic acids, and certain other organic compounds like methyl alcohol, ethyl alcohol, acetone, etc., which, when added to water, even in small amount, decrease the surface tension of water to a considerable extent. Such substances which lower the surface tension of water are called surface active agents. It is for this reason that the soap act as a detergent. For example, if grease is sticking on the surface of a cloth, water does not wet the grease and hence is not removed by water alone. However, if soap is added to water, it lowers the interfacial tension between water and grease. As a result, the grease mixes into the waters, that is soap solution, and hence is removed from the surface of cloth. Fifth is effect of temperature on surface tension. The surface tension of liquids generally decrease with increase of temperature and becomes zero at the critical temperature where the meniscus between the liquid and the vapor decreases. The decrease in surface tension with increase of temperature is obviously due to the fact that with increase of temperature the kinetic energy of the molecules and hence the speed of molecules increases and therefore the intermolecular attraction decreases. An important relationship between temperature and surface tension are as deduced by Eortwas in 1886 is as follows, where lambda multiply m by d to the power 2 by 3 is equals to k Tc minus T, where m is molecular mass of the liquid, d is density of the liquid at temperature T degree Celsius, Tc is critical temperature of the liquid, that is the temperature at which gamma is equals to 0, and gamma is equals to surface tension or surface energy of the liquid at temperature T degree Celsius, and k is a constant. It may be noted that in above relationship, m by d is molar volume of the liquid. If this volume is taken by spherical, then m by d to the power 2 by 3 is molar surface of the liquid, and gamma is the surface energy of the liquid. Therefore, gamma m by d to the power 2 by 3 is molar surface energy of the liquid. Further, Ramsay and Shields in 1893 found that gamma m by d to the power 2 by 3 is 0, not at t is equals to Tc but at T is equals to Tc minus 6, that is at temperature 6 degrees Celsius less than the critical temperature. Hence they modified the equation as follows, gamma m by d power 2 by 3, that is equals to k Tc minus T minus 6. However, according to this equation, gamma will 0 at T is equals to Tc minus 6 and will be negative at T is equals to Tc. To overcome this difficult, Katema suggested a more correct relation, that is gamma m d minus capital D minus small d to the power 2 by 3 is equals to k dash Tc minus T, where D is density of vapor at temperature T. In this equation, gamma is equals to 0 when T is equals to Tc. Now, sixth point is effect of adding increasing amount of soluble substances impurities on surface tension of water. It is observed that presence of other soluble substances impurities affects the surface tension of the liquid considerably. The impurities which tend to concentrate on the surface of the liquid compared to its bulk lower the surface tension. For this reason, substances like soap, detergents, CH3, CH211, SO3 negative, Na positive decrease the surface tension sharply up to cmc and then remains almost unchanged, whereas substances like CH3OH, CH2, CH, C2H5OH, etc. lower the surface tension slightly. Inorganic impurities like KCl are present in bulk of liquid and tend to increase the surface tension of water. The results of different types of impurities on the surface tension are shown. Now next topic is liquid crystals. A large number of organic compounds with long chain molecules, example cholesterol acetate, CH3COO, C27H45, cholesterol benzoate, which formula is C6H5COO, C27H45, ammonium oleate, C17H33, COONH4, etc. are known, which on heating melt sharply to give a milky turbid liquid, which on further heating becomes clear again at a definite temperature. The former temperature is called the transition point, whereas the later is called the melting point. For example, P-azoxyanisole transition point is 389 Kelvin and melting point is 408 Kelvin. On cooling, the clear liquid melt. The reverse changes take place exactly at the same temperature. The turbid liquids thus obtained are found to be anisotropic, a property possessed by crystalline solids, according to which the properties like refractive index, electrical conductivity, etc. are found to be different in different directions. Hence, these turbid liquids are called liquid crystals. However, it is found that the molecules of a liquid crystal do not have the arrangement like that of a crystal lattice. Moreover, except for a few properties like refraction, they behave like true liquids. Example, they possess surface tension and have the property to flow. Hence, in place of liquid crystal, certain other names have been proposed, such as anisotropic liquids or paracrystals. The best name for the substances in this state is mesomorphic state, which in Greek means intermediate state. However, in spite of all this, the original name liquid crystals is still frequently used. Types of liquid crystals now. On the basis of their molecular arrangement, the liquid crystals are classified into following three types. First is nematic liquid crystals. In these crystals, the molecules are lined up in such a way that their long axes are parallel to each other, but the molecules are not arranged in layers. The parallel molecules can slide past each other. The name nematic comes from the Greek word meaning thread, as they appear thread like when seen under a microscope. The crystals are translucent, that is less turbid, and quite mobile, that is can flow. Further, they scatter light strongly. Now next is some examples of the compounds given pneumatic giving pneumatic liquid crystals are given below. The compound is para-azoxyanisole. Transition point is 116 degrees Celsius. Melting point is 135 degrees Celsius. Para-azoxyphenol. Transition point is 137 degrees Celsius and melting point is 167 degrees Celsius. Third is para-methoxycinnamic acid. Transition point is 170 degrees Celsius and melting point is 186 degrees Celsius. Then is dibenzyl benzidine. Transition point is 234 degrees Celsius and melting point is 260 degrees Celsius. Second is smectic liquid crystals. In these crystals, the molecules not only have their long axes parallel to each other but are also arranged in layers. These parallel molecules in planes can split past each other. The name smetic has been derived from the Greek word meaning soap, as these crystals are like soap in touch and structure. These crystals are more turbid and viscous, less mobile than pneumatic liquid crystals. Frequently, a smectic substance is transformed into a pneumatic substance during the course of heating to a higher temperature. Some examples of the compounds yielding smectic types of liquid crystals are given in the table. Compound ethyl para-azoxybenzoate, its transition point is 114 degrees Celsius, melting point is 121 degrees Celsius. Second compound is ethyl para-azoxycinnamate. Transition point 140 degrees Celsius, melting point 249 degrees Celsius. Third is N-acetyl para-azoxycinnamate, whose transition point is 94 degrees Celsius and melting point is 175 degrees Celsius. Third type is clostridic liquid crystals. In these crystals, the arrangement of molecules is similar to that of pneumatic liquid crystals. However, in these crystals, the orientation of the axis shift in a regular way in going from one layer to the next, thereby giving a helical structure. Because of this structure, cholesteric crystals have the remarkable optical property of reflecting light of different colors under different conditions, example at different temperature. Based upon this property, rings using cholesteric liquid crystals are available which change color with person's mood, that is, with one's skin temperature. The name cholesteric have been given to these crystals because these substances are all derivatives of cholesterol but not cholesterol itself. Now, uses of liquid crystals. First uses, liquid crystals are used in wrist watches and other electronic instruments in which a digital display of black number take place against silver background. Second is thin films of cholesteric liquid crystals are used to map skin temperature as an aid to the diagnosis of diseased tissue and in the rings to study person's mood as already explained. Now next topic is difference between liquid crystal, solid and liquid. The main difference between a solid, a liquid and a liquid crystal is in the long range order of their molecules. In a crystalline solid, there is a complete long range order, whereas in a liquid, there is almost complete long range disorder or there is almost no long range order at all. Liquid crystal represents a mesomorphic state, that is, an intermediate state between a solid and a liquid. They do not have a perfectly ordered arrangement of their molecules like that of a solid, still, they have more order than a liquid as observed from X ray diffraction studies. Further, as already mentioned, some crystalline solids on heating from smatic liquid crystals, whereas some other give pneumatic liquid crystals. Both these types of liquid crystals have less order than a solid but greater order than a liquid, and also smatic liquid crystals have more order than the pneumatic liquid crystals. There are some crystalline solids which on heating first form smectic types of liquid crystals, which on further heating become pneumatic type of liquids crystals, which on further heating melt to form the clear liquid. A common example of this type is that of cholesterol myristate. The change may be represented as follows. Cholesterol myristate, if we give 72 degrees Celsius smectic liquid crystals, then given 78 degrees Celsius, it changes to pneumatic liquid crystal. After that, it changes to liquid if 83 degrees Celsius temperature is given to this. Thus, there are two transition temperatures and one melting point. To represent the structural difference between a solid, smectic liquid crystal, pneumatic liquid crystal, and a clear liquid diagrammatically, let us take the example of a crystalline solid of the type of cholesterol myristate. In the crystalline solid, there is a complete long range order in three dimension, that is, all the molecules have the same orientation and have a regular arrangement in different planes as shown in figure. On heating, it forms a turbid liquid called smectic liquid crystal. In this state, all the molecules have the same orientation as they are in equispaced planes, but the arrangement within the planes is irregular as shown. The substance is no longer a true crystal, although it has more order than a liquid. On further heating, the turbidity decreases and a particular temperature, a new state is obtained called pneumatic state. in which molecules still have the same orientation but are no longer in equispaced planes as shown. Thus, more disorder is introduced, yet some order is maintained because all the molecules still have the same orientation. On further heating, even this order is lost and the substance in the liquid state as shown. Now next topic is thermography. It is a technique of recording the temperature variation, especially of the skin on a graph. The record thus obtained is called a thermograph. It is based upon the fact that because of the helical structure of the cholesteric liquid crystals, they have the remarkable optical property of reflecting light of different colors under different temperatures. This is because the helical structure has a characteristic pitch length. These pitch lengths are in the range of the wavelength of visible light. The pitch length changes on changing the temperature, but the chemical structure of the helix remain unaffected. The properties of different liquid crystals are described in terms of event temperature and clearing point temperature. At the lower temperature, where liquid crystals are scattered, visible light is called the event temperature. At the temperature below this temperature, the liquid crystals will be in the solid state and will appear transparent. The temperature above which it becomes pure liquid is called the clearing point temperature. Depending upon the requirement, the suitable liquid crystal can be selected which reflect lights of different colors in the desired temperature range. The most important application of thermography has been in the medical field in the recent years, especially in the early detection or diagnosis of tumor or breast cancer besides orthopedic disorders such as arthritis and back pain, etc. The basic principle is that the heat changes produced in the affected skin are different from the healthy skin. Earlier, the physicians used to paint the liquid crystals on the portion of the body to be examined, but the method was too rough. Now, this method is simple. The liquid crystals are pressed against the healthier part as well as the part to be examined, and the color photographs are taken of the resulting patterns of colors and then compared. In fact, the principle of thermology has been in use since very early times. Ancient Greek physicians employed a primitive method of thermology, that is, they used to apply a thin mud slurry onto the areas of their patient's body and observe the pattern of drying and thereby determine the abnormal distribution of body heat. This technique was called medical thermology. Now next topic is liquid crystal display, that is LCD and 7 segment cells. One of the most important application of liquid crystals, smectic and nematic type, has been in the electronic industry. They are being used in thin lightweight display devices such as digital watches, pocket calculators and similar instruments. As this is done with the help of liquid crystals, it is called liquid crystal display LCD. The basic principle is as follows. A thin film of liquid crystal, not more than 1,000th of an inch thick, is placed between two sheets of a glass, one of which is coated on one side with a thin layer of an electrically conductive material such as tin oxide. When no current is passing through the conductive coating, the molecules are uniformly oriented and the light can pass through the cell. When the current is applied, the molecular alignment changes because the liquid crystal molecules are polar and the cell appears opaque or black. Thus, a number or a letter is displayed in black against a silvery background. As liquid crystal display requires a very small current, that is, it consumes very little power, electronic watches and calculators run for years with a small battery. Most of the displays in LCD watches and calculators are composed of several 7 segment sections. Each 7 segment section can display one number. The combination of these sections display the numbers. Similarly, for alphanumeric display, there are 14 segments. A segment means an active area in the display or image area. The complete display panel is composed of two polarizers that transmit light in perpendicular direction, a mirrored surface, and a layer of liquid crystal material between two glass plates as shown. In absence of the applied voltage, the liquid crystal molecules in all segments are precisely aligned. Therefore, the entire panel appears silvery because light passes through both the polarizers reflected back by the mirrored surface and then again passes through both the polarizers. When voltage is applied to the segment of a display, the precise alignment of the liquid crystal molecules is lost. This results in the polarized light from the first polarizer not being rotated by a required 90 degree to align the second polarizer. The second polarizer blocks the passage of light and causes that segment of the panel to appear black.